We're now going to start covering the bridge pattern. The objectives in this discussion are to help you understand the bridge pattern, its common roles and responsibilities and consequences and so on, as well as how to understand how to recognize ways in which the bridge pattern can be applied to make the expression tree structure easier to access and evolve transparently. The purpose of using the bridge pattern is to help decouple the expression tree programming API from its behavior and implementation, and as well as to enable transparent extensibility. By using bridge, we'll be able to minimize the coupling between clients, abstractions, and implementations. Let's start by discussing the context when we apply this to the expression tree processing app. Our expression tree processing app is going to need to run in a range of different design time and runtime environments. For example, we'll have mobile devices with limited memory and processing power versus laptops and desktops, which have a lot more abundant resources at their disposal. So as a result, we want to be able to find a way to minimize the impact of variability on our design. We don't want to have to tightly couple application components to a particular environment or a particular service, because this is going to yield suboptimal implementations. For example, our composite node implementation that we talked about before has a rich inheritance hierarchy. And that may actually be problematic in some cases where we might want to have things be a bit more concise in certain ways to reduce overhead of virtual methods, to reduce the number of classes involved, the surface area of the design, and so forth. So we'd like to make it possible to be able to replace one implementation with another without breaking any commitments we have to existing client code. Another issue is we don't want to end up with inflexible service behavior. We'd like to be able, for example, to keep the implementation fixed while varying certain properties of the service itself. We might want to be able to transparently add instrumentation for every call to an expression tree operation to log it in some way. Likewise, we might also want to be able to transparently add synchronization to certain expression tree contexts where we may be running in a multi-threaded environment. Once again, we want to be able to enhance the service behavior that's exposed without breaking the implementation we have. The solution we're going to apply will be to separate an abstraction from its implementation or implementations. And the goal is to be able to encapsulate variability behind a stable API that creates separate class hierarchies for an abstraction and its implementations. As you'll see, we're going to be able to vary not only different implementations, but also different abstractions as well, using the approach we're going to discuss here. We'll have variations in how the expression tree is implemented, as well as variations in how the service is provided to the application. To do this, we're going to end up having the client be able to call to an abstraction that internally forwards that call to the corresponding implementer subclass that's been designated for that particular configuration. So for every call to a method in the abstraction, which in our case will be called expression tree, it will go ahead and forward it to the appropriate implementation that's part of our composite hierarchy. So for example, if someone calls the accept method on the expression tree, that will turn around and forward to the appropriate accept method that's part of the designated composite implementation. We can then go ahead and also subclass the abstraction class to create different behaviors or services without actually affecting the implementer hierarchy. As you can see here, we subclass from expression tree to create an instrumented expression tree that wraps before and after logging messages around each call that's been forwarded to the underlying composite method with the same name. Similarly, we can go ahead and create a synchronized expression tree that refines the expression tree interface so that every method that's invoked will turn around and grab a lock using the synchronized keyword in Java that will acquire that lock, then forward the operation down to the potentially non-thread safe implementation hierarchy subclass, and then release the lock after that method call is done. The particular way we're going to implement this and realize this in Java is to define an expression tree class, which defines an abstraction that shields the clients from the implementation details of expression trees that may change at design time or even at runtime. There's a number of methods in this class. Some of the methods look very similar to ones we had earlier in the composite hierarchy, the item method, the left method, the right method, and so on. These are all forwarded down to the appropriate implementation method in the implementation hierarchy. Another method can be used to pass in the root of the implementer hierarchy so we can configure the expression tree with the appropriate composite hierarchy at runtime. There's also the accept method, which is going to be used later when we talk about the iterator and visitor pattern in order to be able to do operations in an open-ended way on the expression tree. And finally, there's also another method here that's important. That's the make iterator method. This is actually a factory method that's used to create iterators, and we're going to be using this as a way to differentiate various parts of our design to get different ways to traverse the tree. It's also, as we'll talk about later when we talk about implementation, it's also something that differentiates the use of the bridge pattern, which we're focusing on here, from other related gang of four patterns, such as decorator. From a commonality and variability point of view, this particular expression tree interface provides a common API for the operations that are available on an expression tree. And then we go ahead and we can use subclassing either of the expression tree interface itself or the component node hierarchy that it's connected to. Depending on various factors, we can vary these things based on user input, the options that are set, the iterator behavior we want, the expression tree representation. All these things can change, and yet the interface that's seen by the clients remains stable. Once again, this is not just a random collection of classes. It's actually something that follows one of the key gang of four patterns called bridge. The intent of the bridge pattern is to separate an interface from its implementation or implementations so the two can vary independently. You should consider applying bridge under a number of circumstances. When the abstraction and the extensible implementation can vary independently of each other, as was the case in our particular expression tree example, as well as when there's a need to change the implementer hierarchy at design time or runtime without breaking client code. We don't want to have the clients be modified when the implementation hierarchy details happen to change. Let's take a look at the structure and participation in this particular pattern, and we'll map it back to our expression tree case study. One of the key roles you have is something called the abstraction. This is the interface that's used by the client. In our case, we're going to represent this via the expression tree class we just looked at, and it'll define a set of operations that are exposed to the application. We then have an implementer hierarchy, and of course there's a root base class of the implementer hierarchy, which is going to be forwarded from all the calls the client makes on operations on the abstraction. So when an operation is called on the abstraction, that turns around and forwards through a pointer to the appropriate implementation subclass. In our case, the implementation root base class is component node. And then we can go ahead and subclass to provide various specialized or customized implementations of that particular abstraction. In our case, we have component unary node, component binary node, component add node, component negate node, and so on and so forth. These are all nodes that override the base class operations to do more specialized kinds of things. And finally, there's also something called a refined abstraction, which can be used if there's some reason you want to vary the abstraction itself orthogonally or independently from the implementation that's part of the implementer hierarchy. In our case, we could have synchronized expression trees, instrumented expression trees, and so on and so forth. Let's now take a look at how you might implement the bridge pattern in Java. We're going to use this to separate the expression tree abstraction from the composite implementer hierarchy. So we define an expression tree, and we have a number of fields and methods defined there. We can put a component node root data member that stores the root of the composite implementer hierarchy. We can have a constructor that passes in that root and stores it in the field that's private to the expression tree objects. And then we can also go ahead and define various methods. In this case, this is the accept method. There's other ones, of course, as well, like left, right, item, and so on. The accept method is used to forward down to the implementer via the field called root. We can then go ahead and create different kinds of abstractions by subclassing from expression tree. We can make an instrumented expression tree. And I show a simple example here where we're going to have the accept method do some logging operations before and after it calls the accept method. Here's a similar example for another refined abstraction called a synchronized expression tree, which inherits from expression tree, and its methods, like accept, will have synchronized blocks placed around the calls to the appropriate method that's defined in the expression tree. All of these things can be done in a way that doesn't affect the implementation hierarchy, but only refines the abstraction interface. Here's an example of how we could actually put these pieces together from a client perspective in order to be able to use the expression tree that we construct. As you see here, we can go ahead and create a particular expression tree. We'll keep a real simple example here. We're going to create an expression tree that has a composite add node with two leaf nodes that adds together the numbers 3 and 4. And as you can see here, the way we do this is once we create the composite portion using the component node hierarchy, that's all hidden behind the expression tree abstraction, which is part of the stable API that's offered by the bridge pattern. If we turn out we want to replace a different implementation later, change the implementation to use a tree node-like structure as opposed to a composite node-like structure, we don't have to make any changes to the client code per se. We just have to change the way we create the expression tree composite and connect it into the expression tree abstraction. In practice, of course, we wouldn't hard code the creation of the expression tree. We'd use some kind of creational pattern. For example, we could have some kind of factory method that might be used to abstract away from the details of how you make an expression tree. And something else we'll take a look at later is we'll actually see how we can apply the builder pattern to create the composite implementation in a more sophisticated manner. Regardless, however, of how we create the expression tree, whether we create it by using the factory method, hard coding it, do it by some kind of builder pattern, and so on and so forth, the nice thing about Bridge is we can now write application code that won't change regardless of how the tree is structured internally. For example, here's a very simple illustration of where we can have an iterator that will walk through every element in an expression tree and do something with each of the nodes, and we don't expose those details because those are hidden by the abstraction that's offered by the bridge. A little foreshadowing of what we'll cover later, it's worth pointing out that we also apply the iterator, strategy, and visitor patterns to this example too, and we'll cover them as the time comes along. So let's go ahead and take a quick look now at some code written in Java from the expression tree processing app so you can get a better feeling for how it works and how it's realized in an actual programming language. We implement the code for the bridge pattern using the expression tree class. Let's take a look at how it's implemented. As you can see, expression tree is just a simple public class. Internally, it stores the root of the component node composite hierarchy, which actually keeps track of the contents of the nodes in the tree. Down here, you can see we have a constructor that takes in a component node and stashes it away inside the root data member. Most of the methods in this class simply forward through this root reference to the underlying implementation that corresponds to what's used in the composite itself. For example, here's the item method, which simply forwards to the root item method to return that. Likewise, the left and right methods on expression tree create corresponding expression trees from the left and right children that are accessed through the root. Most interesting of all is the accept method, which also forwards to the underlying composite element via the component node reference. And that's what actually does the work for the double dispatch we'll talk about later when we discuss the visitor pattern. One more piece that's worth mentioning here is the make iterator factory method. This method takes in a string containing the traversal order request, and it uses the tree iterator factory to go ahead and create an instance of the appropriate iterator strategy. We'll talk later when we talk about the iterator pattern and the strategy pattern and the factory method pattern, how this particular piece of code works. But this is just enough to get you started now. Let me now show you an example of a refined abstraction that inherits from expression tree to provide a slightly different type of service. As you can see here, instrumented expression tree extends expression tree, and all of its methods do some before and after work when delegating down to the actual implementation. For example, let's take a look down here at the accept method. As you can see, when the accept method is called on the instrumented expression tree refined abstraction, it first prints out a logging message that it's starting the accept call, then it delegates to the expression tree's accept method, and finally it prints out that it's finished doing the accept call. Naturally, you could put more sophisticated type of logging into your solution in order to be able to provide more information about the logging itself. Here's another example of this idea of refined abstraction. This is the synchronized expression tree, which extends expression tree. What it does is all of its methods use synchronized blocks in order to be able to provide thread-safe access to the underlying composite data structure, which itself is not thread-safe. We have not made any attempt to try to put locking or synchronization into those methods. Here's an example of the accept method. As you can see, we come in, we synchronize on the this pointer, and then we go ahead and forward to the superclass's accept method, which ends up calling expression trees accept. And when that call returns, the synchronized block automatically releases a lock. So as you can see, the bridge pattern is very straightforward to implement. Doesn't really do a whole lot. As we mentioned in various places throughout this sublesson. Bridge in Java has less importance than it does in other languages like C++, but this gives you a feeling for how to implement it. Now that we're done discussing a bit of the implementation of the bridge pattern in our expression tree processing app, let's discuss some of the consequences of applying this pattern in practice. There's a number of benefits that comes from using this pattern. One benefit is that the abstraction and implementer hierarchy are decoupled, so they're able to evolve separately by applying the so-called open-closed principle. The open-closed principle is a very famous object-oriented design principle that enables software to be open for extension, say via the implementer hierarchy we've talked about here, and yet closed for modification by having a stable abstraction API. And so you're kind of able to get the best of both worlds. You can have the dependability and stability of a fixed interface, and yet you can also vary that interface in ways that allow things to evolve and change over time. And the bridge pattern works very, very nicely to implement the open-close principle. If you want to be able to extend the behavior of the application, we can add new code through subclassing without having to break or change the existing code. Another nice consequence of applying the bridge pattern is that implementations or implementers can vary at design time or runtime. We don't have to hard code things. We can make those changed later on. And one of the other nice things you'll typically see is this behavior works in the context of applying various creational patterns. So the details of how things are actually made are also abstracted and hidden as well. There are some potential downsides to using this pattern, however. One of the downsides is there's a one-size-fits-all abstraction interface. Things have to fit into the Procrustean bed of a common set of methods with a common set of signatures. And if you're in an environment where that doesn't really conform to what you're doing, you may find the bridge pattern a bit limiting. It turns out in practice that you can often alleviate some of the implications of this one-size-fits-allness by applying other patterns, such as the Gang of Four adapter pattern, which allows software components to work together even if they weren't originally designed to have the same interface. It's a good pattern to take a look at. We're not going to cover adapter in detail in this particular course, but it's worth understanding, and you use it a lot in practice to make things fit together in a common way. There's a number of interesting implementation details to consider when you try to apply the bridge pattern. One of the key issues is how do you create the right abstraction and/or the right implementation? In practice, this is often done by using creational patterns like factory method or builder. You may end up having various ways of creating the appropriate implementer hierarchy nodes. In our case, this would be things like the various composite multiply nodes or leaf nodes or other kinds of nodes. And we can do that in a way that's abstracted away from the client's interface or the client's access. We'll cover Builder later and show how it can be used to create composite expression tree nodes. Another consideration, which is important in languages that don't have the kind of garbage collection you find in Java or C#, is to share implementations and do reference count. For example, in C++ or Boost, there are various concepts like shared pointers, which can be used in a very powerful way to some extent automate the reclamation of memory when an object is no longer used. It's kind of a poor man's garbage collection for languages that lack that feature as a built-in capability. In this particular approach, you can use this to reference count various implementations. You might reference count composite add nodes or composite multiply nodes. And the expression tree interfaces are responsible for keeping track of the reference counting. And when the reference count drops to 0, the object is automatically disposed of. Clearly, this is going to come up much more commonly in a language like C++ than it would in Java. There are situations, of course, in Java where you may want to share things as well. You may want to share common sub-expressions, and so reference countings could still apply there, but you'd have to do this by yourself. It's not really built into the library of Java. If you need more dynamic uses of bridge, you may want to consider other Gang of Four patterns, such as Decorator. Decorator and bridge have quite a bit in common. They have a very common looking structure. In some cases, they're both trying to solve a very similar problem. You're trying to extend or enhance certain capabilities by having a common interface. The main difference between the two patterns is that Decorator is most commonly used in situations where you want to be able to take something and wrap dynamically different enhancements over top of an existing interface. If you take a look at the Gang of Four book, they talk about the use of Decorator in the context of being able to encapsulate various kinds of window widgets in a graphical user interface environment. So you can take a window and you can wrap a scroll bar or a border around it in various ways. So it's a bit more dynamic, it's a bit more complicated than bridge. I usually end up using bridge when I try to do these kinds of things. I have very rarely used decorator, but if you have that need for dynamism and dynamically extending things, you might want to take a look at the decorator. There's lots of different known uses. As I mentioned before, bridge is very heavily used in C++, not so heavily used in Java. There are some examples of using bridge in Java. One interesting example comes from the Java socket programming API, where you have this concept of a socket implementation, which corresponds to different platforms like Windows versus Unix and so on. And then you have the actual socket abstraction itself, and that provides a set of services that is used by users of sockets. And in that case, you can take socket service abstraction and then be able to do things like add support for compression or various kinds of security and authentication protocols in a way that's independent of whether or not you're implementing this on top of Windows sockets or Unix sockets and so on. So it's a good example of bridge. If you take a look at the socket interface, you can see where in Java you can actually plug in a sock impl or socket impl that is used to actually provide the implementation, which is then delegated to by the abstraction portion of the socket. There are lots of other examples as well. Oftentimes in Java, people don't use bridge, and instead what they do is they use interfaces and factories to get much of the same effect. So that's a somewhat lighter weight way of being able to do things. From my perspective, if you're programming in Java and you're not planning to have much refined abstraction, then the bridge pattern is probably superfluous and you're better off using interfaces and factories to get much the same effect. So to summarize this pattern, bridge decouples the expression tree programming API from its behavior and implementation, and it enables transparent extensibility. I should also mention that a very common pattern compound in practice is bridge composite. We use the composite in order to be able to have the diversity of different types of nodes in some recursively composed design. And then we can hide all those implementation details behind a nice, simple, stable bridge abstraction, which itself can be customized and extended and refined in various ways independently of the way in which the details of the composite work. So this is a nice example of two gang of four patterns that we sometimes see used together, and so we can talk about them as a compound, bridge composite.